In the vast universe, there are plenty of mysteries, and one that has puzzled astronomers for a long time is the concept of dark matter. Dark matter constitutes 27% of the universe, but despite powerful telescopes like the James Webb Space Telescope, scientists have been unable to detect its presence. Recently, however, something unexpected has occurred, a theory that completely rejects the existence of dark matter and challenges our understanding of this mysterious substance that permeates the universe. Interestingly, this theory is endorsed by the legendary physicist Sir Roger Penrose, who believes that dark matter doesn't exist. So why is this theory forcing scientists to re-evaluate the standard model of cosmology? Why does Sir Roger Penrose believe that dark matter doesn't exist? Let's find out. Dark matter seems to be out there dominating the material of the universe. It's by far the majority of the universe's substance, but nobody really knows what it is. It seems to be the major part of a galaxy's mass. It was first observed because the stars were orbiting too fast for the visible matter alone to account for the gravitational attraction, indicating the presence of something else. Various cosmological observations confirm its presence. If it exists and if gravity is responsible, there's nothing else in physics affecting its mass, which is estimated to be around the Planck mass, about 10 to the power of -5 g, roughly the mass of a flea's eye. This mass is huge when considering particle physics. Now imagine looking at the night sky filled with galaxies, stars, and cosmic wonders. It's a breathtaking view. But did you know that what you see is only a small part of the cosmic story? Dark matter, as its name suggests, doesn't shine or emit light, nor does it interact with forces that allow us to observe celestial objects. Nearly invisible, it's believed to make up about 27% of the universe's mass. This enigma has puzzled scientists for years, and its existence is inferred from gravitational effects on the visible universe. Think of the universe as a jigsaw puzzle. Dark matter is the missing piece. Though we can't see the piece, we know it's there because of the gap it fills. The mystery deepens as, despite our belief in dark matter, we're unsure what it's made of or how it behaves in particle physics. No elementary particle represents dark matter, leaving scientists searching for something elusive. Various candidates for dark matter have been suggested, from weakly interacting massive particles to actions and sterile neutrinos. These are like missing characters in a cosmic story, and scientists have embarked on a quest to find them. Large experiments like the Large Hadron Collider, LHC, and projects such as CSST, LU, Zeppelin, and the Axion Dark Matter experiment have tried to capture these elusive particles. Despite years of searching, these efforts have mostly yielded silence. The lack of direct evidence has led to a profound question. What if dark matter isn't the answer? What if it's not the missing puzzle piece, but rather a gap in our understanding of the universe's fundamental forces? This is where the theory of AQUL comes in. Instead of persistently searching for dark matter particles, AQUL proposes we rethink how gravity works on cosmic scales. Isaac Newton's gravity has explained the movements of celestial bodies reliably, but AQUL suggests we need to adjust the laws of gravity at cosmic distances and low accelerations. AQUL, which stands for quadratic iron, changes Newtonian gravity by introducing a new perspective. This theory suggests that on cosmic scales, especially in regions of very low accelerations, gravity behaves differently than classical physics predicts. It's like adjusting our perspective on the cosmos, searching for new angles to understand its mysteries. This quest for alternatives like AQUL stems from scientists' relentless curiosity and their determination to uncover cosmic secrets. For nearly a century, dark matter has been used to explain gravitational anomalies in galaxies, but the lack of direct evidence has made us reconsider our approach. The exploration of AQUL and similar theories isn't a dismissal of the well-established dark matter model, but rather a challenge to it. It's a question that scientists are bold enough to ask. What if our understanding of the universe is incomplete, and the missing piece isn't in the cosmos but in our comprehension of its fundamental forces? The exploration of modified gravity theories isn't a rejection of the fundamental principles of gravitational physics laid down by Isaac Newton. Instead, it's an effort to enhance and expand our understanding of gravity under specific cosmic conditions. These theories become relevant when we delve into the realm of cosmic scales and ultra-low accelerations, where traditional gravitational laws may need adjustments to explain observations. The M theory, introduced in 1983 by Israeli physicist Mordechai Milgram, suggests that instead of searching for invisible particles like dark matter, we should consider altering our understanding of how gravity functions in regions with extremely low accelerations. Milgram recognizes that Newton's laws of gravity, which work well in high-acceleration environments like our solar system, may not perfectly describe the dynamics of galaxies and galaxy clusters. A key concept in M is the introduction of a threshold acceleration, marking the point below which gravity begins to behave differently from what classical physics predicts. M implies that when accelerations are below this threshold, we need to adjust our gravitational laws to account for the observed behavior of celestial objects. It's like seeing the rules change when transitioning from playing marbles to playing chess. Different games, different rules. AQUL, or quadratic iron, is an extension and refinement of MOND, modified Newtonian dynamics, proposed in 1984 by Milgram and Jacob Bekenstein. It builds upon the core concept of M, introducing a new mathematical framework to describe how gravity operates at very low accelerations. The central innovation in AQUL is the introduction of a modified iron, which is a function representing the difference between the observed gravitational force and the force predicted by classical Newtonian gravity. The iron in AQUL involves a general function and the threshold acceleration term. In essence, AQUL suggests that gravity behaves differently in regions with extremely low accelerations compared to high acceleration systems, like having a specialized set of rules for a unique cosmic arena. The key distinction between traditional gravity and modified gravity theories like AQUL lies in how they scale with cosmic distances and accelerations. In familiar high-acceleration environments such as our solar system, Newton's laws of gravity remain an excellent description, having been rigorously tested and verified over centuries. However, as we venture into the vast reaches of the universe, particularly when examining the dynamics of galaxies and galaxy clusters, we encounter significantly lower accelerations, navigating new terrain where the old maps no longer suffice. This is where M and AQUL come into play. Let's consider the cosmic landscape from an M-AQUL perspective. When observing the behavior of stars at the outer edges of galaxies or in the vast void of cosmic structures, we encounter accelerations that are orders of magnitude lower than those experienced in the solar system. In these cosmic outskirts, the standard gravitational rules begin to lose their explanatory power. M's key insight is that below a certain critical acceleration, gravity no longer scales linearly with distance. Instead, it starts to scale closer to the square root of the distance, accounting for the unusual galactic rotation curves observed by astronomers like Vera Rubin. AQUL takes this idea a step further. Instead of directly modifying how gravity scales with distance, it introduces the concept of an iron, defining the difference between the observed gravitational force and the one predicted by traditional gravity laws. The iron function depends on distance and the threshold acceleration. So what are the implications of these modifications to the laws of gravity at cosmic scales? The core of MOND and AQUL is to provide a better explanation for the observed behavior of galaxies without the need for dark matter. By redefining how gravity operates in low-acceleration environments, these theories offer an alternative explanation for phenomena like galaxy rotation curves. The primary advantage of AQUL over MOND lies in its more sophisticated mathematical framework, making it a refined and more comprehensive theory. AQUL, with its iron description, provides a more detailed and nuanced explanation of how gravity works in cosmic settings with ultra-low accelerations. This added mathematical complexity positions AQUL as a comprehensive alternative to dark matter, addressing some of MOND's limitations. To grasp AQUL's significance, let's compare it to the traditional dark matter model. In the standard dark matter framework, the presence of dark matter is invoked to account for the peculiarities observed in galaxy motion, particularly the fact that outer regions rotate nearly as fast as inner ones. The dark matter model attributes this behavior to the gravitational influence of unseen particles. AQUL, however, suggests that the transition between a galaxy's inner and outer regions results from changes in the velocity distribution of stars, not the presence of invisible matter. AQUL proposes that the observed kinks in galactic rotation curves arise from the galaxy's inherent dynamics, not the gravitational pull of dark matter. A crucial turning point in AQUL's examination occurred with a study by KHC. This research aimed to determine how well AQUL could explain both the inner and outer portions of galaxy rotation curves using data from 152 galaxies in the Spitzer Photometry and Accurate Rotation Curves SPARC database. The study compared the observed centripetal acceleration of particles in motion with the expected Newtonian acceleration derived from the distribution of baryonic matter in the galaxies, primarily consisting of stars and dust. The study yielded enlightening results. AQUL provided a better fit to the SPARC data than the conventional dark matter model. This suggested that AQUL could potentially offer a more accurate explanation for the observed behavior of galaxies, particularly the differences between inner and outer rotation curves. However, a critical factor emerged: cosmic mean external fields. The study underscored that AQUIL produced accurate predictions for both inner and outer rotation curves only when the cosmic mean external field was considered. This external field represents the influence of distant cosmic structures, like massive galaxy clusters, on observed galactic dynamics. The inclusion of the cosmic mean external field in AQUIL further highlights the theory's capacity to account for cosmic intricacies, emphasizing the intricate interplay between local galactic dynamics and the broader cosmic environment. While AQUIL's performance in explaining galaxy rotation curves is promising, it's crucial to acknowledge that no scientific theory is without its limitations. AQUIL, like all theories, has its own set of challenges and shortcomings. One notable limitation is AQUIL's inability to fully explain observed gravitational lensing by galaxies, where a massive gravitational pull bends the path of light from background objects. The way this bending occurs has been significant evidence for the presence of dark matter. While AQUIL excels in explaining rotation curves, it may not entirely address the phenomenon of gravitational lensing. The exploration of AQUIL and its potential as an alternative to dark matter represents a significant stride in the ongoing quest to unravel cosmic mysteries. It encourages us to rethink our understanding of gravity and its behavior in the vast reaches of the universe. While AQUIL may not have all the answers, it stands as a bold leap in the realm of modified gravity theories, offering a fresh perspective on how the cosmos operates.